Okay, good. So let's get started. Yeah. So so far we have seen what is divide and conquer approach. And under this divide and conquer approach, we have two sorting algorithms. One is merge sort and second one is quick sort. Merge sort we have already covered in the previous class. In this class, we'll talk about quick sort. Okay. So let's see what it is. So quicksort, what is the idea behind this? Quicksort is a divide and conquer algorithm, as I told you just now. So if it is a divide and conquer algorithm, definitely there will be two steps. One is divide and other one is conquer, right? So in divide step, what we are going to do here, so let me explain you here. Carefully see this. So let's say you have an array or a list, fine, and you have elements present in this array, fine. Okay. So what we are going to do in this quicksort algorithm, we will be having something called as pivot. Some people call as pivot, some call as pivot, but most commonly it is pronounced as pivot element. Okay. So we have something called as pivot element. Okay. So what we do generally, usually you can say we select the first element as pivot element. We can select last element as well. We can select randomly also, right? Or we can select the median of this, entire array, right? But as of now, just for simplicity, understand that we are considering first element of the array as the pivot element. Clear so far? Okay. So here, if you see in this one, what we are saying in divide step, choose an item P known as pivot and partition the items of A of I to J into two parts. So let's say this is your I and this is your J. Okay. So you have an array which is having elements, or you can see the indexes are from I to J, right? I is the starting index and J is the last index. Okay. Now you are going to select a element P, that is your pivot element, in such a way that this pivot element will partition this array. Let's say one more is there. Okay. Yeah. So let's say it will partition this array in such a way, or you can say in two parts basically, in two parts. And how these two parts will be partitioned? So what is going to happen? So let's say this is your pivot element, right? Initially you are going to select first element as the pivot element, but in the actual sorted array, carefully listen this, in the actual sorted array, this pivot element will be present somewhere, you know at this position, not exactly at the middle, but it may be in the middle, it may not be. Okay, depends where it is going to be placed in the sorted array. But what I want to convey here is that the left part of this and the right part of this. So the left part of this, so this pivot element will partition the array in such a way that in the left portion, whatever elements you are having, that will be less than equal to P. That means in the left part, all the elements will be lesser or equal to pivot element. Understood? Similarly, in the right part, whatever elements you are going to have will be greater than the pivot element. This pivot element will be partitioning this array in this particular manner. Are you getting the idea? Right? We will see how it is being done. Everything we will discuss in detail, but this is what we are going to do. Okay, so let's see here. So choose an item P known as pivot and partition the items of array of I to J into two parts. The first part, items that are smaller than P and items that are greater than or equal to P. See, sometimes, if you refer multiple resources, somewhere they will consider, the elements on the left smaller than equal to P, right? And the right, on the right, elements are greater than P. Somewhere they mention, they consider the right part as, the equal part also, greater than equal to, and the left part just the smaller part. Okay, so that is not going to create any problem. You can consider whatever you want. Okay, is this clear? So this is how you are going to divide it. Fine. And recursively sort the two parts. So now you have two parts, right? This left part is there and right part is there. So you are going to sort these two parts recursively. Now, how we are going to do it, you will understand. Just give me some time to explain you. So this is what we are going to do in this divide step, and then we have the conquer step in which you don't have to do anything. Okay. So if you remember, if we compare this with the merge sort, right? I told you in the merge sort, what is the core of the merge sort? The merge algorithm itself, right? The merge algorithm that we have in the merge sort, that is the core or the most important part of the merge sort, right? So, and where we have that, merge algorithm, that is in the conquer step. If you remember, that is present in the conquer step in merge sort. But here, if you see, so in merge sort, we are spending most of the time in the conquer step, which is having this merge algorithm. But if you carefully see here, in the quick sort, it is kind of opposite. The most of the time, or you can say almost the entire time, we will be spending in the divide step itself. Okay, so this is the difference between merge sort and quick sort in the way of idea how we are going to implement. It is different. Both the sorting algorithms are different, but it is based on divide and conquer approach. So this is the one of the difference between these two. Okay, so now let's try to understand this through this example or illustration. Okay, so this visualization will really help you to understand what is happening, and we'll see one more example that is going to be there in the implementation part. Okay, so let's focus on the divide step, what we are doing in this quick sort. Carefully see this. This array is given to you. It's an unsorted array, right? Now what we are doing is we are selecting the first element as the pivot element. So here it is 27, right? So what we are going to do then, we are going to partition this array, we are going to partition about the pivot 27. That means around this we are going to partition it. So if I'm going to partition this one, so as I told you, on the left of pivot, you will be having all the elements less than that. It may not be sorted. It may happen that those are unsorted, but all the elements will be less than the pivot element. As you can see in this example, 12 and 16 are present on the left side of the pivot element, that is 27. And whatever elements are present on the right, all these elements are greater than or equal to this pivot element, right? In this example, they have considered it like this. Okay. Then what we are going to do further? Then we are going to further select this portion and this portion. Carefully understand this. This is the most important part of this. So once you select this pivot element, now you have left part and you have right part. In the left part itself, so let me explain you here now. In the left part itself, you have 12 and 16, right? Now what you are going to do, in this one also, you are going to select this pivot element. So the same partition algorithm will be applied on the left part, and say similarly the partition algorithm will be applied on the right part. So you have 39, you have 27, and you have 28 or what, 38. Okay, so here you will be selecting this pivot element. So if you have this 12 as the pivot element, obviously 16 will be present on the right of 12 because it is greater, right? So it will be present on the right of 12. Now can I say these are sorted itself? Because if you have a single element in the list or the array, they are already sorted, right? So this part is done. What about this right part? Carefully see this. In this one also, I'm going to select the first element as the pivot element. Partition algorithm will be applied on the right part now. So what will happen? You have 39 here. 27 is less than 39, right? So it should be present somewhere here. Let me write it in this way. So 39 is present over here. 27 should be present here. And 38 should be present here, right? So now if you carefully see, if you see, now we have these two things, right? So around the pivot we have placed all the elements, whether it is less or whether it is greater. So here we have now this array. So again on this one also I will be applying this partition algorithm, because now this is left of this pivot element, right? So on this I'm going to apply, so recursively, this is how recursively we are applying the partition algorithm again and again till we get the single element in the linked list or no element in the linked list, or the linked list is basically empty. Till that thing, that is the base case basically, then we are going to keep on applying this partition algorithm. So now I will select this first one as the pivot element, right? So what will happen? We have 27 here. Obviously 38 is greater than 27, so I'm going to have 38 here. So now they are single element linked list, not linked list, single element list or array, so they are sorted. And we have 39 over here, this 27 is already here. So this is how we are going to return, this is how we are going to return the entire sorted array. Is this clear? Do you have any doubt so far? So you understood, right, what we are doing? How we are going to do this, you will see in the implementation part. Okay, let's proceed. So this is how we are going to get the sorted array, right? So you notice anything special about this position of pivot element in the final sorted items? Yes, the special part is whatever is on the left, that is smaller than that, whatever is on the right, that is greater than or equal to that. Clear? That is the that is one thing we can notice here. Okay, now let's talk about the implementation. So as far as implementation is concerned, I will explain you. So this code that I'm explaining here, that is in C++. Okay, but you don't have to worry at all. I have also included one Python code in the slides that you can refer. But to get a clear idea, see, you I hope you also know this, or if you, even if you don't know, Python abstracts few things, right? When you are implementing any logic through Python, it abstracts a lot of things, right? Sometimes if you are seeing a Python code, you find a little hard, right? It is easy to write the code, that is true, but sometimes it abstracts or it hides the important concepts, right? So as I know multiple languages, so I can tell you this. So, and you will see the difference also. So try to understand this and you will easily understand this. There is no rocket science here. It's simple code, right? It's, you can consider it as a pseudo code, and you have already seen such kind of codes in the previous classes also, right? So we'll see both the codes, and then you can make a difference, like how things are being done in this C++ and in Python also. Fine, let's start. So let's see the implementation part here. We have a function here, void quicksort. Void means it is not going to return anything, right? This is a return type basically. Okay, so what we are doing, just as simple as that, we are providing one array to it, right? We are providing a low and a high. What is low and high? Low is the starting first index of the array, and high is the last index of the array. These three things we are providing as the input, or as the arguments or the parameters to this function. Understood? Yes. Now what we are going to do is, we will have a condition here. If low is less than high, if low is less than high, till that we are going to execute this one, right? This is the condition, because there should be some condition when to stop, right? So if low is going to cross high, then we can definitely stop, right? Okay, so if low is less than high, we are going to call this partition function here. Okay, partition function, as the name suggests, it is basically partitioning the array. It is going to divide the array. So this is the divide step. And what we are passing initially to this partition function, the same thing. We are going to pass the array, we are going to pass the low index, we are going to pass the high index. And what it is going to return, it is going to return the index of the pivot item or pivot element. Is this clear? It is going to return the actual correct position of that pivot element. That means the index of the pivot element. Clear? And then we are calling this. So basically, let's assume somehow this partition function is providing you the actual index of the pivot element. Okay, that means the correct position of the pivot element. Now after that, what we can do, Can I say I can recursively call this quick sort on the left part and on the right part? That's what we are doing. So we are calling this quick sort function recursively. Recursive call is there. We are passing the entire array. That is true. Or you can say the array. So basically, array name is nothing but here the address of the array, right? The starting address. So we are providing that array, and we are providing. So this is, we are applying the quick sort on the left part. So low index is there and pivot index -1 just before that. So can I say the left part is done, right? We have applied the quick sort on the left part. Similarly, if I want to apply the quick sort on the right part, so what I'm going to do, I'm going to provide this array and pivot index +1. So we are not including that pivot index because we know it already, right? Pivot index, the next to it, right? So pivot index +1 up to high, right? That means the high index is also there. Is there any doubt in this code that is given to you? Simple, right? Crystal clear? Okay. So we are recursively calling the two portions, left portion and right portion. The same thing is mentioned over here as well. And pivot item does not, there is no need to participate in further sorting because it is already sorted. We have the pivot index. That means we have the correct position of the pivot element. So it doesn't have to participate again in the sorting, right? Fine. Let's proceed. Now comes the crux of this quick sort, that is the partition function. What we are doing here actually, right? Carefully see this. So you have seen what we are doing, but how we are going to do that, you will see here. Carefully see this now. Quick sort, the partition algorithm. So to partition a of I comma I up to j, not comma, I up to j, we choose a of I as the pivot p. That means the first element as the pivot element. Okay. Why choose a of I? Are there any other choices? Yes, there are other choices as well. We can select first element as the pivot. We can select last element as the pivot. We can select random element also as the pivot. And we can select the median of the array as the pivot. Okay. So if you do low plus high divide by 2, whatever index you get, you can consider that element as the pivot element as well. But for simplicity and for some obvious reasons also, because I will tell you why we are usually select first or last element. Okay. You will understand this. Carefully see this. Okay. So we have selected the pivot element as the first one. Okay. The remaining items, carefully see this now. The remaining items means I plus 1 up to j. So once first element is selected as pivot, the remaining items in the array are divided into 3 regions. So carefully see this here. We have divided this entire array, the remaining elements, into 3 regions: S1, S2 and unknown. You will understand what it is. S1 says a of I plus 1 up to m, where items less than p. Okay, so I plus 1 up to m, some m index is there. So it shows whatever elements you have in this particular bucket or in this region are less than the pivot element. Fine. What about S2? A of m plus 1 up to k minus 1, where items are greater than equal to p. That means greater than the pivot element, greater or equal to the pivot element. Okay. What about this unknown region? So unknown region is unprocessed region. That means still those items which are present in this unknown region, we have not decided yet, or we have not processed them so far. We have not processed them yet, like whether it will be assigned to the S1 bucket or S2 region. Clear? So can I say initially, once I select the pivot element, can I say the entire remaining elements actually initially are in the unknown region only? Yes or no? Because still initially, just at the initial step, I can say, because still so far I have not processed all the elements. So remaining elements are in the unknown region as of now. Understood? Any doubt in this particular slide? Okay, so I'm going very slow and I just want to make sure that in one go you understand each and everything, and definitely you will. Okay, so here also it is mentioned initially regions S1 and S2 are empty. All items excluding the pivot element are in the unknown region. Okay. For each item A of k in the unknown region, so let's say we pick one element from the unknown region. Let's say the next, whatever is the next element that we have next to the pivot element, I pick that element from the unknown region and I compare that with P. Obviously, then only I can decide whether it is less than or greater than pivot element. Yes. So if A of k is greater than or equal to P, that means it is greater than or equal to the pivot element. Can I say I will put that into the S2 region? Yes, as simple as that. Otherwise, I will put that into the S1 region. Understood? This is also very clear, straightforward. Okay. Now, what is the case one here? Case one says if A of k is greater than or equal to P, just now what we have seen. So that element will be put into S2. So here's the visualization. If A of k, which is a y element, y is greater than or equal to P. So I can say initially it was, carefully see this, initially y is in the unknown region. Yes or no? A of k is element y that is in the unknown region. Once I compare this with the pivot element, I can say, yes, if this case is true, then it will belong to S2 region. What I'm going to do, carefully observe this. I have incremented k. I have incremented k. Once I increment k, can I say that y element will be part of S2 now, not the unknown region? Correct? Okay, let's proceed then. What about the other case? If A of k is less than P, if A of k, let's say it is y, just for the denotation, we have used this. So it is less than P, then it should be part of S1 bucket or S1 region. But how we are going to make sure that it becomes part of S1 region? So carefully see this. Till M we have this S1, right? Because from M plus 1, S2 starts. So y is present over here at k index. What I'm going to do is I'm going to increment M. So I incremented M. Once I incremented M, can I say M is now pointing to this X, some element. I don't know what it is, but some element is there. Okay. Now what I'm going to do, I'm going to swap these X and Y, because so far I don't know what, I don't know about X, right? Whether it is less than or equal to, I don't know, right? Or let's say still if it is, part of S2, it is greater than. So if it is greater than, I can still move it on the right side. I don't have any issue, right? So I swapped X and Y comes here and X comes here. So can I say now I have made sure that if this case is true, Y becomes part of S1? Yes or no? And then I'm going to simply increment K, because now unknown has to be moved forward, the unknown first index. Any issues, any doubt in this particular slide? Both of you clear? Okay, good. Let's proceed. So now we are going to see the code of this, how we are. So far we have seen what we are doing, but how we are going to implement it. Carefully see this. This is your partition function here. As I told you initially, we are providing the array I and j, which is nothing but the low and high initially. But this will change as you are going to call this partition again and again. This I and j will definitely change, right? So this code is there. We'll understand this code. This example is there. To execute this code, now we have this particular example over here. Oh, what happened? Uh, oh, uh, I think I lost whatever I had written before, right? Some, by mistake I clicked that cross here, but it's fine, right? Okay. Yeah, so basically I just underlined things, right? I didn't write anything specifically, and whatever is there in on the whiteboard, it is there. Fine. Okay, so what we are going to do now, so we have this code here and we have this example here. We will dry run this code on this particular example to understand it in a clear way. Okay, so let's say this partition is there. Int p is equal to a of I. It simply says the first element. We are saying this as a pivot element, p element. Okay, carefully see this. So here I is there. Fine, I is there. So this is your pivot element, not I, P, right? Sorry. So pivot element P is there. It is already written, so fine. Okay. Now int M is equal to I. What we are doing now, when I'm saying int M is equal to I. So by this, what we are making sure? We are making sure that we are storing the pivot index. Yes or no? Initially, wherever it is present, we are storing the pivot index. Why? Because we may have to move that pivot element from that position to its correct position. So we are storing that index into some variable, integer variable. Fine. Let's proceed. For int k is equal to I plus 1. So initially I told you, right, remaining all elements will fall in unknown bucket initially. So k will starting from here because k is equal to I plus 1. And it will go up to the end. Okay, fine. Let's see this condition now. If a of k is less than p, it simply says whether this element is less than the pivot element or not. 38 is less than 27. The answer is no. If condition will become false. Else part, do nothing. Do nothing. Simply increment k, because obviously if it is greater than pivot element, it has to be on the right side only, right? So we don't have to do anything. Fine. We move forward. Now we are present over here. Now k is there. See, after understanding this code, and once you see the Python code, you will say, sir, why you have explained all these things? Why not just the Python code? It's so simple. Okay, but still I want you to understand this in a clear way so that you feel confident that I know the algorithm, actual algorithm, how it is being implemented. Okay, so k is incremented. Fine. If a of k is less than p, if a of k is less than p, 12 is less than the pivot element, answer is yes. Condition becomes true. What I'm going to do now, m plus plus. So now I moved my m also, right? I have incremented m also. You will understand why we have incremented m. So now m is present over here. This index, 38 element index, right? Now we are swapping a of k and a of m. A of k and a of m. So I have swapped 12 with 38. Carefully say this now. Now 12 is in S1 because I know that S1 will consist of what? S1 will consist of all those elements which are less than the pivot element. S2 will consist of all those elements which are greater than the pivot element. Clear? Okay. Fine. Let's increment again. K. Let's increment again. K is now here. The grade area. 39. 39 compare with the pivot element. Is it less than that? No. Though, so do nothing. Just proceed. Do nothing means you can assume that it is present now in S2, right? Because it is greater. So now we can say we have processed this element. It is in S2. Nowhere we are having this S1, S2 in the code, but it's just for our understanding purpose. Okay. So we have incremented again. Now 27. 27 is less than 27? No. So do nothing. Just proceed. I hope this is also visible to you. Oh, what happened? Why we are facing so much issue today? Okay. Just a minute. Can we move it somewhere? Okay, now I think it's fine. Okay, now I can see this. So we have moved k also. Now k is present over here. If a of k is less than p, 16 is less than 27? Yes. So what to do? Increment m. So once you increment m, m will be here. M will be here now. So you swap a of k and a of m. Swap it, 16 with 38. You get this. Is this clear? Because what we are doing, we are making sure that whatever is less than the pivot element, it should be present in the S1 bucket. So we have shifted that. Now what else? Can I say this for loop will exit now? Because we have scanned the entire array? Yes. Now swap a of I comma a of m. M is present over here. A of I, it is here. Swap these two elements, because now once we swap this, what we are making sure, see, m is that integer which is the end of the S1 region, right? So if you swap those elements, can I say the pivot element will be placed just at the end of S1, you can say, or at that place. So it will make sure that pivot element will come at the correct position. Now this will return m. So finally we'll get m here. So this m is keeping the track of the pivot element once we are storing that, or once we are placing that at the correct position. Now what do we have? Now we have the left part, apply quicksort on the left part, recursive call, apply quicksort on the right part, recursive call. Is this clear? And once you call quicksort on the left part, again, can I say again the same, this will execute, because now for this left part, the I and j will change. Now I will be 0, but j will be just pivot index -1, or you can say m -1 also, correct? So the next call that is going to happen, so quick sort on left, so that is a I and m -1, and the right part, a m +1 j. Is this clear? Any doubt in this? It's not difficult, right? Once you understand it clearly, it's not difficult. It's simple, straightforward. That was your quick sort. As simple as that. Let's talk about the analysis. Any doubt so far? Clear, right? Okay. Let's talk about the partition analysis. So if you remember, in case of merge sort, we calculated, or we computed how many times merge is being called, right? If you remember, how many times merge is being called. Similarly here, we will see how many times partition is being called, because that will decide the complexity. Okay, so the partition analysis. In the partition analysis, if you see the code, how many loops are there? Only one loop is there, for loop. Okay, so can I say it is almost scanning the entire array, right? So can I say it is going to be order of n? The complexity is going to be order of n for this for loop. Similar to merge sort, the complexity is then dependent upon the number of times partition is called, right? So here also it is the same. Basically in merge sort we call this merge, right? Okay. Now, so we can say that it is order of n times, but we have to see how many levels would be there, right? Because if you carefully understand this, let me explain you here. What is happening here? Carefully see this. You have the array here, which is having n elements. You selected one pivot element, and after one, calling partition on this, what is happening? Can I say you are getting something like this? You have the pivot element at its correct position, and you have divided the array into two halves, right? Just ignore the pivot element as of now. We can say that it is dividing the array into two halves. Further, if I call partition on these left part and right part, again I can say it will divide into two halves, and this will continue. This will continue until we get the single element list or array, right? So how many levels will be there? Can I say, first of all, before even talking about levels, what is the amount of work done is happening here? Can I say it is order of n only? Because partition will be applied. What about here? Again, it is going to be, so divided into two halves, right? One partition call is there, divided into two equal halves, and size is n by 2. Amount of work done, order of n. What about here? Here, two partition calls are there, right? And two equal halves, but the size is n by 4 now. So again, amount of work done is order of n. So can I say at every level the amount of work done is order of n? How many levels would be there? The same concept that we have already seen in the merge sort. N, then n by 2, then n by 4, right? Like this. So it will go up to when this thing becomes equal to 1 single element list or array, right? So k will be what? The number of levels will be log n. This thing we have already seen, so I'm not explaining in detail. This thing we have already seen in the previous class in merge sort. So the number of levels will be log n. When this is happening, carefully understand this. When this is happening, can I say this is happening only when your pivot element that you are selecting is approximately partitioning the original array into equal halves? Yes or no? Then only it is happening. If somehow in some scenario, if it is not doing so, if your pivot element that you are selecting is not dividing the array or partitioning the array into two equal halves approximately, then this is not going to be the number of levels, and we'll discuss that case as well. But before that, is this clear so far? Any doubt? Number of levels will be log n. So if number of levels is log n, so we can say this: the total time complexity will be n at every level. Number of levels is log n. So it is going to be n log n. Is this clear so far? Do you have any doubt? Simple? Okay. Let's proceed. Now let's talk about the worst case analysis. What can be the worst case analysis here? See, for every other sorting algorithm, just remember whatever sorting algorithm you have seen so far: insertion sort, bubble sort, selection sort, and even merge sort as well. Let's go back in the reverse order. Merge sort. What can be the best case? There is already sorted. Yes or no? There is already sorted. That is going to be the best case for all the algorithms, right? So if the array is already sorted, merge sort still takes order of n log n time. We have seen this already, whether it is a best, average, or worst. Correct. What about selection sort? If you give a sorted array to selection sort, still it will take order of n square time. Correct? Still it will take order of n square time. Yes. In all three cases, it takes order of n square time in case of selection sort. In case of bubble sort, if I'm talking about unoptimized bubble sort, the by default bubble sort, that will also take order of n square. But if I discuss the optimized version, in best case, if I have the sorted array already, then it takes order of n. Yes or no? In case of insertion sort, in case of best case, when you have the array already sorted, then also it will take order of n time. Correct? So you understood, right? Like whenever I'm talking about the best case, the one thing that comes into your mind will be best case for those algorithms is the array is already sorted. Correct? But this is different in case of quick sort. And what is that? The thing is, let me explain you here first. Let's say you have a sorted array already given to you. Maybe let's say 2, 6, 9, 11, 13. Let's say this is given to you. What you did, you selected this as the pivot element, right? Okay, this is your pivot element. Now just tell me, once you call the partition on this, what will happen? No change, because that is already present at its correct position. Okay, fine. So what next? In the next, you will call, because this is done, right? This is done. Pivot is placed at its correct position, right? Now, can I say you will select this as a pivot element now? Yes. What will happen now? Because now this is the array, right? The remaining part. Again, the same thing. No change. Fine. This is also done. Select this one. No change. This is also done. No change. This is also done. No change. What is happening here? You had the array of size n over here in the first partition. When you call the first partition, what is happening? You have one element here, that pivot element. The remaining is your n minus 1. Now again you are calling partition on this. Pivot element will be selected. One element will be separate it out, and you will be having n minus 2 elements now. Again one element, n minus 3 now. And this will go on up to when you have a single element in the list. What we can observe here, can I say initially you have these many elements to sort, then you have n minus 1, then you have n minus 2, n minus 3, and so on up to 1. And that will give you what? N into n plus 1 by 2. So can I say the worst case for quicksort, worst case is the array is already sorted. So in that case, the time complexity of quicksort will become order of n square. This is very important point. Questions can be framed on this. Now carefully say this. Worst case analysis of quicksort. When the array is already in ascending order, pivot element selected, remaining element as it is. What is the pivot index returned by the partition? The first index only, right? S1 is empty while S2 contains every item except the pivot. So this is what is happening now. N1, n minus 1, then n minus 2 up to 1 contains the pivot only. So total number of levels here will be what? N, not log n, because it is not dividing it into equal halves. So that is the reason the time complexity. So as you can read here, as each partition takes linear time, the algorithm in its worst case has n levels, and at every level you are doing what? N, order of n amount of work, right? So n into n will be your order of n square. Clear? What about best and average case analysis? Best case would be what for quicksort? When it is dividing into two equal halves. That is the best case for quicksort, right? And partition always splits the array into two equal halves. Depth of the recursion, that means the number of levels will be log n, and complexity will become order of n log n. In practice, worst case is rare, and that is true, right? Because it is very rare that you are going to get the sorted array and you are applying quicksort on it, right? So getting the worst case is rare. On the average, we get some good splits and some bad ones. For average case, it may happen that sometimes we are getting equal number of halves, but again after applying recursive calls, maybe you are not getting equal number of halves. So good splits and bad splits can happen, right? But still the average time will be your order of n log n only, because that will balance out basically. Clear? So what is the lower bound? Comparison based sort. All the algorithms that we have covered, right? All are comparison based sorting algorithms. Whether you talk about insertion, selection, bubble, merge, quick, because we are doing comparison only, right, in these algorithms. So all comparison based sorting algorithms have a complexity lower bound of n log n. What does that mean? That means in worst case complexity, for worst case complexity, you cannot go below this n log n. That is the best you can achieve. Is this clear so far? Rashtra is asking, when will this time complexity will be order of n here? In this quicksort, you are saying? Not possible. Not possible. That's what I'm saying, right? You cannot go below n log n. That is the best you can do. For comparison-based sorting algorithms, you cannot go below n log n. You have one non-comparing based sorting algorithm. Partition analysis. See, partition algorithm is part of quicksort. Partition algorithm itself is taking order of n time, right? So at every level you are doing partition, right? That's what I explained you here. Where it is. Here it is, right? At every level you are doing partition, right? You are dividing the array into two halves. So at every level you are doing this much amount of work, right? Order of n. Here also 1 into 2 into n by 2, because n by 2 of 2 two equal halves of n by 2, and one partition call is there. That's why you got this. So at every level you are doing order of n. But how many levels are there? Log n levels are there, right? Log n levels are there. So n into log n is the time complexity of the entire quicksort algorithm. And you cannot go, if you talk about comparison based sorting algorithms that we have discussed in the entire section of sorting algorithms so far, all are comparison based. You cannot go beyond n log n. If I talk about worst case, therefore any comparison based sorting algorithm will with worst case complexity is optimal n log n. We have, there are many algorithms, but we have one non-comparison based sorting algorithm, which is radix sort. That is not there in your syllabus, but in that scenario, it for that the worst case complexity is in order of n times. But again, that is not in your syllabus. So maybe after the gate exam, if you really want to learn, you can learn radix sort as well, or other sorting algorithms also after the gate exam. As of now, it is not required. Clear? Okay. Yeah, let's see the Python code now. What happened? Yeah. Okay. Carefully see this. The Python code. Just this code is there for the entire quicksort. What is happening here? Quicksort method is there, defined function is there. You are passing just the array, correct? If length of the array, what is the base case here? If length of the array is less than equal to 1, what does that mean? Either the array is empty or the array is having only one element. In that case, you simply return the array. As simple as that. Otherwise, you are selecting pivot element as array of -1. What we are doing here, what is the pivot element here? That is the last element. In this one, it is selecting last element. Obviously, you can select first element also. Array of -1, right? I hope you know this. That will give you the last element of the array. Okay, so then what we are doing? So yeah, so then we are having these two, left and right. We are maintaining these list, right? Do you know list comprehension in Python? There is a concept, list comprehension, in Python. Again, important concept in Python. So what we do basically here, so we can write something like this. So as of like simply when we write for x in array, right? Let's say we want to basically get all we want to get all the elements in the array, right? So one by one it is going to select. But if I write x here, like here it is mentioned, right? X for x in array. So in that case, this is kind of, in a single line, you can write the entire for loop. And then you can write the condition here also, like if x is less than 10, right? If this condition satisfies, whatever elements you are going to pick, if this condition satisfies, that you can store somewhere in another list, right? Some in another list. So let's say if it is maybe L, just L is there, L is equal to this, right? So based on this condition, the elements will be selected and stored in this particular list. This is list comprehension. Okay, so we are maintaining one left list and right list. What is the condition here? X for x in array from beginning till the end. So you are scanning the entire array. If x is less than equal to pivot element, then what you do, you place all those in the left. And in right, from again, scan the entire. If x is greater than pivot, all the elements which are greater than pivot element, store in the right list. Done. Your partition is done. Partition algorithm. 2 lines of code. Okay. And then what you are doing? You are simply calling recursively quicksort on left and quicksort on right. And you are basically concatenating all the elements that you are going to get from these recursive calls along with the pivot. That's it. That was your code in Python for quicksort. Simple, right? Very simple. But again, like if I shown you this code directly, you would not have understand the quicksort algorithm, the beauty of the quicksort algorithm. Yes or no? That's why I decided to explain you the C++ code, because there you get the actual feeling of what quicksort is doing, right? And now you can definitely, just for coding purpose, you can definitely refer to this code. But here you will not understand much. There are a lot of things that is abstracted completely. Okay. So all the sorting algorithms we have covered completely. Now properties of sorting already I explained to you, but I thought of adding these in the slides as well for your reference later on if you want to just refer or for revision purpose. In place sorting, or sorting algorithm is said to be in place if it does not require any extra space. So order of one time. Merge sort is not in place. Why? Because we use, by default, merge sort is not in place because we use extra space, right? Extra list or extra array we store for the result. Is quicksort in place? What do you think? Yes or no? The answer is yes, it is in place. We haven't used any extra space, right? If you go back to the code again, even if you see here, are we using some any extra space? No, we are simply doing everything in the array. If you see this code, the C++ code also, we are not returning anything. Here we are returning the index, and there we are, all the operations that we are performing, that is there in the original array itself, right? We are not having any separate extra space. Clear? So quicksort is in place. Stable sorting, another property of sorting algorithms. If the relative order of elements with the same key value is preserved by the algorithm, then we can say it is stable. Now let me ask you, what do you think? Is quicksort a stable algorithm? What do you think? Is quicksort a stable algorithm? The answer is no. The answer is no. See, we are not doing one by one comparison of the elements, right? If you again go to the previous, like the code, the implementation that I've explained to you for quicksort, we are swapping the elements, right? So whenever you are doing swapping, right, in selection sort also, directly we swap the minimum element, right? So whenever you have swapping like this from one place to another place, then for those algorithms you won't find it stable, right? If you have duplicate elements, and you can take one example also, try to apply quicksort, you will find it out that the order is not sure, like your order will not be preserved if you have same elements present in the array or the list. So quicksort is not stable, but it is in place. Clear? Any doubt in this? Okay. So for your revision purpose, I have added this table also, the summary of all the algorithms that we have discussed. Selection, worst case order of n square, best case order of n square. In place, yes. Stable, no. Insertion, order of n square, best order of n. Both in place and stable. Bubble sort by default, order of n square on square, yes, yes. Bubble sort 2, that is 2.0, optimized version. In best case, it will take order of n, yes, yes. Merge sort, n log n in all the cases, but it is not in place. But with slight modifications, we can make it in place as well. But by default, it is not. Stable, yes, because the relative order is maintained. One by one comparison we are doing, right? If you remember the merge sort algorithm, if you can recall it. Quick sort, order of n square, order of n log n in best case. In worst case, you know what is the worst case. Keep this thing in mind. A question can be framed for worst case of quick sort, right? Obviously, they won't ask you directly the time complexity, but some question can be framed. There is one question in GATE computer science based on this quick sort, and there they have included the probability concept. So you can find that question. If not, let me know. I will give you that question. Okay. That is a really good question they framed on this quick sort. Okay. So make sure that you solve that question. So yeah, n log n, and it is in place, but it is not stable. So this is the summary of all the algorithms that is there in your syllabus and that we have covered in lot of detail. And that was your subject done from my side. So how was the entire subject of